Hello guys, and welcome to another calculus video. In this video we're going to be taking on these two cool trigonometric integrals, both with sine of x. And yeah, that's pretty much it, so let's go ahead and jump right into the video. So this first integral I think is pretty cool because it looks almost as if we have this integral from 0 to pi over 2 of sine of x plus 100 tangent x over sine of x. And we can already see that some things are going to cancel, and obviously this 100 is not a number that you see very often on math, so it's pretty safe to guess that no matter what number we would put there, probably positive number, we would get the same answer. And so it's kind of interesting because it's almost as if that tangent x wasn't there, right? So let's go ahead and solve this integral real quick. We're going to just expand it using the angle addition formula here. So we're going to get the integral from 0 to pi over 2 of cosine of 100 tangent x plus we're going to have cotangent, I guess, cotangent of x, because we're going to have cosine over sine times sine of 100 tangent x dx. And so here, I'm thinking what I'm going to do here is just u equals tangent x, because then we get a nice integral from 0 to infinity. So we're going to get the integral from 0 to infinity of cosine of 100u over 1 plus u squared from our differential, plus sine of 100u over u times 1 plus u squared, because cotangent x is just 1 over tangent x. And now I think the interesting thing here is cosine, this integral right here, integral from 0 to infinity of cosine of au over 1 plus u squared du. It's a pretty famous one. I've solved it before on the channel, so I'm not going to go ahead and solve it here, but it's equal to pi over 2 times e to the negative a. It's absolute value of a, but here we're talking about a greater than 0, so I'm just going to leave that as e to the negative a. And so that actually helps us to evaluate this other one right here, because if we let f of a equal the integral from 0 to infinity of sine of au over u times 1 plus u squared du, we get that f prime of a is equal to the integral from 0 to infinity of cosine au over 1 plus u squared, because that u cancels from the chain rule, which is just pi over 2 times e to the negative a. If we go ahead and integrate, we're going to get that f of a equals pi over 2 minus pi over 2 e to the negative a plus c. And when we solve for c, we're going to find that f of a is going to equal pi over 2 times 1 minus e to the negative a. And so essentially here we have this right here, evaluated at 100, and this evaluated at 100, so we have pi over 2 times 1 minus e to the negative 100 plus e to the negative 100, right? When we add these two together, and they're just going to end up canceling, and so our answer is pi over 2, which is the same as if we had just sine of x over x, right? Or sine of x over sine of x, which I think is pretty interesting. So that's a cool one. And now let's go ahead and solve our other integrals. So the second problem that we're going to be solving here is the integral from 0 to 1 of sine squared of x minus square root pi squared minus x squared dx. And as you can see here, we're going to probably want to normalize this a little bit. Oh, sorry, this is the integral from 0 to pi, not 0 to 1. So I don't like this pi squared minus x squared. I prefer to have 1 minus x squared, so I'm going to go ahead and substitute x equals pi u dx equals pi du, right? So we're going to end up with pi times the integral from 0 to 1 of sine squared of pi times u plus square root 1 minus u squared, minus sign. This is all du. Next, we don't like sine squared. I'm just going to go ahead and power reduce right now. So we're going to end up with pi times the integral from 0 to 1 of 1/2 plus 1/2 cosine, blah, blah, blah. So this part, 1/2, when we integrate it, we're just going to get 1/2, right? So I can bring that all the way outside. We're going to get pi over 2 plus pi over 2 times the integral of cosine of 2 pi times u minus square root 1 minus u squared du. All right, nice. Now what we're going to want to do is actually, I'm going to call this I1, and we know that our integral I is going to equal pi over 2 plus pi over 2 I1. We're going to go ahead and evaluate I1. Alright, so the first thing we're going to do here is, since we have this x and square root 1 minus x squared, I'm just going to go ahead and substitute x equals sine theta. So we're going to get integral from 0 to pi over 2 of cosine 2 pi sine theta, and then this is going to become cosine theta, and our differential is going to be cosine theta d theta. Now, something that I notice here is it's obviously really nice to have this cosine theta right here, because it makes me think u equals sine theta, right? But of course that's a problem because we have this cosine theta that then becomes annoying to deal with. So what if, instead of cosine theta there, out on the outside, we had a sine theta? So if we could put sine theta right there, then it would also be pretty easy to deal with, because we could substitute u equals cosine theta. But then again, we'd have this sine theta that's nasty to deal with. So we want on the outside not cosine theta or sine theta, but cosine plus sine theta or cosine minus sine theta, right? So we're going to go ahead and try to do that by substituting u equals pi over 2 minus x, and then I'm just going to pi over 2 minus theta, I guess. Yeah, let me fix that right there, pi over 2 minus theta. And then I'm just going to rename the variable back, because... So, and what that's going to do for us is, on the inside, this is going to become cosine theta minus sine theta, or cosine u minus sine u, take your pick. But since we're taking the cosine of all of that, cosine of negative x is just cosine of x, so we just keep that the same. So we're going to end up with integral from 0 to pi over 2 cosine of 2 pi times sine, I'm just going to rename the variable back to theta, minus cosine theta. And then instead of multiplying by cosine theta, since we substituted u equals pi over 2 minus, we're going to get sine theta, d theta. Now, of course, both of these are equal to I1, right? And if we add these two integrals together, we're going to get that 2I1 is equal to the integral from 0 to pi over 2 of cosine 2 pi sine theta minus cosine theta, all times sine theta plus cosine theta. And notice that the derivative of sine theta minus cosine theta is just sine theta plus cosine theta, because of how you differentiate those functions. So we can go ahead and just integrate like that. So we're going to have, when we integrate cosine, we're going to get positive sine, so 1 over 2 pi sine of 2 pi times sine theta minus cosine theta, evaluated at pi over 2 and at 0. But notice here that when we evaluate this at pi over 2, the inside right here is just going to be 1, because this is 0 and this is 1, and when we evaluate this at 0, the inside is going to be negative 1. And in both cases, we have sine 2 pi, so it's going to be sine of 2 pi and sine of negative 2 pi, both of which are 0. So this whole thing just goes to 0. So this whole integral actually goes to 0. I1 is equal to 0 as well. And so that means that our integral I is just equal to pi over 2. I hope you guys enjoyed this video. We have some shorter integrals this time, I know, but I thought they were pretty interesting. I've been taking them out of a new source that I'm getting integrals from, and I'm having a lot of fun with these integrals. So if you want to see more, please let me know. If you want to see something different, I'm always open to suggestions, and yeah, hope you enjoyed the video, and I'll see you next time.